Hello and welcome to the video about our paper. Our paper is called Machine Learning and Email Classification, Naive Bayes and Support Vector Machine Method. Jessica and myself worked on this. What if you were to log into your email every day and see hundreds upon hundreds of emails, only to take a closer look and see that 90% of them are unwanted or spam emails? It would be overwhelming and annoying. There are filtration systems already in place, and this is something that is interesting to us. We researched and found that two commonly used filtration systems are Naive Bayes and Support Vector Machine. We researched these two systems further to better understand email classification.
Many different methods have been used to classify spam in the past. In our literature review, we looked at two main methods. First, we looked at the naive Bayes method, which implements an algorithm that uses the probability of our hypothesis the data is spam given the data, which may be like the frequency of a token word appearing in the email. There are different types of naive Bayes methods, and in this paper we specifically discuss the flexible Bayes and the multinomial Bayes method with Boolean attributes.
Second, we looked at the support vector machine approach to classifying email. This method takes vectors that contain the attributes of the email that are appointed by the user and converts them into single points on a Cartesian plane. It then decides the best hyperplane to divide the dataset into two parts, spam or not spam. It then evaluates each email according to the division due to the hyperplane. We have chosen this topic because of its relevance to our lives. Everything is electronic nowadays, yet we usually don't know how things work. We knew that there were systems in place to filter out emails, but we wanted to understand how it worked, so we researched this topic.
Our current neural network is designed for pattern recognition and determines whether an email sample is spam based upon its associated attributes. The internal architecture contains two layers and uses different functions to transform the data. The functions include the sigmoid symmetric transfer function and the sigmoid transfer function. In this video, we will discuss other methods that can be used instead of these specific neural network functions to transform data and classify emails. One of the methods that we researched in our literature review was the naive Bayes method. Some naive Bayes methods consider the frequency of certain words appearing in emails to help determine whether or not an email is spam. There are several different types of naive Bayes classification methods, but we focused on the two for which the authors of the article we read received the best results. The first one we discuss is the flexible Bayes method. In the first step of the algorithm, we would create a dictionary containing tokens, keywords or symbols that would be flags for spam that would be found in the emails. Second, we would pre-process the data in our 4,501 samples to scale it down and reduce irrelevant factors. Then we would iterate through the emails one by one and apply the flexible Bayes method to determine the probability that an email is spam. The formulas that we are using come from an article that we read, Spam Filtering with Naive Bayes, Which Naive Bayes? As opposed to using a single normal distribution, the flexible naive Bayes method averages several normal distributions of each attribute of the emails to determine the probability that an email is spam. Hence, the function sums up the normal distributions from 1 to LIC, where L sub IC is the number of different values x sub I that an attribute may take on. C stands for the category, so essentially this equation looks at the likelihood of an email having a certain value of an attribute given that it is categorized as spam or not spam. For the multinomial naive Bayes method, steps 2 and 3 are like steps 1 and 2 from the flexible naive Bayes method. Since a prerequisite for multinomial naive Bayes method is to have all Boolean attributes, we needed an additional first step that involves either changing our non-Boolean attributes to be Boolean or removing all non-Boolean attributes, or some of them. We could possibly make our non-Boolean attributes Boolean by creating a mathematical comparison, such as if a certain word appears at least once, which would evaluate to true or false, giving a Boolean value. Then we would proceed with step 2 of creating a dictionary containing the token words and pre-processing the data by applying the ratio factor just as we did with the flexible Bayes method. Finally, for every email, we would apply the multinomial naive Bayes method for Boolean attributes. We'll show the formulas on the next slide. The top formula shown is the multinomial distribution. In this formula, the value d is the message, and it can be represented by a vector x bar containing 57 values representing the occurrence of token t in the message d. Since these are Boolean attributes, we would expect to see 1s and 0s in this vector. The second formula is the criterion that determines whether or not an incoming email is spam. Here, capital T is equal to 0.5, since we are classifying an email as spam if it has a probability of at least 0.5. The last formula shows the probability of T sub I given category C. This is used in the two above equations just discussed. In this equation, N sub Tc is the number of occurrences of token T, the keyword or symbol, in the training messages of a respective category C. For example, if given that an email falls into the spam category, we would calculate the probability that a certain token would appear in that email with this formula.
The other method that we researched in our literature review was the support vector machine method. The first step to implementing this method would be to convert the vectors into a single data point. The second step is to plot the points on a Cartesian plane. Then we would go through each and every email from 1 to 4,501 and have a line divide the dataset into two. We would then evaluate how many spam emails are on one side and how many not spam emails are on the other side. The last step would be to find the maximum score from step 3, and that would be the hyperplane. These are the equations we would use to implement the support vector machine method. The first equation is taken from an article by Lazurka and Leon. This is the equation they have implemented to find the best hyperplane to divide the dataset. L is the number of emails we are given, x, y is the data point of the email, W is the hyperplane we are trying to find, and C is a user-selected regularization parameter. They converted the formula into the dual kernel function due to the very large number of training vectors and problem dimensions. It was more efficient and easier to use this function. This is our function box. On the right-hand side are the inputs to our function, which includes the email and the 57 attributes of each email, as well as the dictionary that has the established words that we identified as token words for spam. The transformation part of the box is our neural network hidden layer map. The 57 attributes are all going to the 10 hidden layers. On the left-hand side are the outputs. Our neural network will be outputting whether the email is spam or not. And now a live demonstration of our code. This is our neural network already developed. We wanted to get either a 0 or a 1, so we added to the output code the MATLAB function round. If the percentage is 0.5 or above, it will output a 1. If the percentage is 0.49 or below, it will output a 0. I will grab the data from the Excel sheet, create new variables, and run these variables through our neural network. These were the 100 data samples that we withheld from the original 4,601 data points. We created our neural network with the 4,501 data points and kept 100 points for testing, 50 spam and 50 not spam. First, I will create a new vector of the not spam data points from the Excel sheet and run it through our neural network. As you can see, our neural network can determine which emails are not spam quite well, only getting 2 out of the 50 data points incorrect. This is a 96% accuracy. Now I will do the same thing, but for our spam data points. Here I am inputting the spam data points by creating a new variable, and now I will run it through our neural network. Our neural network is not as good at determining which emails are spam. It has determined that 10 of the spam emails are not spam, giving this an 80% accuracy. There is still room for improvement on our neural network.
As shown in our presentation, the neural network accurately categorized the majority of test spam emails correctly and virtually all the test non-spam emails correctly. The improved performance was accomplished by recognizing patterns in similar samples and scaling certain attributes of the data. However, we could improve the ability for our neural network to correctly categorize spam. Of the naive Bayes method and SVM method we examined in the literature, we believe that the SVM method would be the better of the two approaches that would improve our results, since the margin of error of this method is normally lower than any other classification method. Our neural network could also be improved by adjusting the neural network architecture itself. For example, we could remove attributes that seem irrelevant to the data for some improvement. However, more significant changes are predicted if we were to add deeper layers to the network. As an area of further study, we could consider comparing the ability of the Bayesian and frequentist approaches to classify spam. These are opposing methods that make different assumptions. Bayes' assumptions lead to the correct answer much more often, however. Frequentist statistics were discussed briefly during our forecasting class, and even though we predict that Bayes will perform better, we potentially can gain a better understanding of the naive Bayes method and Bayesian statistics in general by comparing it to an algorithm unlike it.